Thank you very much. I'm David Pui from the Particle Technology Laboratory at the University of Minnesota. So today I would like to share with you some of our recent research in agglomerate measurement. Now, large quantity of nanoparticle agglomerates, such as diesel particulate and engineered nanoparticles, are produced in large quantity. And we like to have information of their particle size, morphology, and concentration, which are essential for nanoparticle property, health effects, emission control, and abatement. Now, most of the state-of-the-art measurement technology deliver only the equivalent spheres of mobility, aerodynamic diameter. However, we all know that most of the real-life particles are loose agglomerates, particularly with the diesel and engineered nanoparticles, so that there's a need to develop technique for measuring this type of nanoparticles. So a few years ago, my colleague and I, we did some penetration measurement of spherical particle and multiple wall carbon nanotubes through stainless steel screen. This 20 micron opening. And we find that the penetration of the sphere and carbon nanotubes deviate a great deal. So this suggests that perhaps this could be a method to classify the sphere versus agglomerates. Now, it turns out that we find out that it doesn't work too well for agglomerates, nanoparticle agglomerates. So we then go to a smaller size nuclear pore type of filter media, and that works. For example, this is about 1 micron nuclear pore openings, and we are collecting some of the 350 nanometer diameter silver. You can clearly see that some of those agglomerates are intercepted at the opening of the pore. So we further developed that, and to try to make use of this technique for fractal dimension, length measurement, and so on. So this is how we do that. We put the fresh engineered nanoparticles into a mixing chamber to have them agglomerate to different fractal dimensions, and then we classify with a DMA. And after that, we neutralize the particle and send it to the filter holder, where we put the nuclear pore filter, and we measure upstream and downstream simply using a condensation particle counter. Now, if you look at the right-hand curve here, the top one is for sodium chloride near spherical particle, and then the second one is a soot particle, the black symbols. Third one is silver agglomerates, the red one, and then the purple ones are for the carbon nanotubes. You can see that there's a clear separation between particles of different fractal dimensions. So next, we pass a particle of known fractal dimensions through a 1 micron pore diameter nuclear pore filter at the 5 centimeter per second phase velocity. Now we can measure the penetration as a function of the mobility diameter, and you can see that from a sphere, near sphere 3, fractal dimension 3, 2.9, 2.6, and down to this 2.1, and then the green one are the carbon nanotubes. So they separate very nicely, and the standard deviation are relatively narrow. So we feel that this could be a technique that could allow us to pre-classify these nanoparticle agglomerates. So in this latest paper that just came out, we proposed a technique of making use of this to measure nanoparticle length and fractal dimension. For example, let's say that if we have a mobility diameter of 100 nanometer, and if it has, let's say, 16% penetration through the 1 micron nuclear pore filter, and this will give us a length of 200 nanometer and a fractal dimension of 2.1. So these lines are for different fractal dimension. So the details of this technique is in this paper. So moving on, to measure the surface area of a sphere first, and then followed by agglomerates. Now, some years back, Heinz Fissan and we have worked on a nanoparticle surface area monitor, and which consists of a unipolar charger followed by a electrometer. And now this is the performance of the instrument. The red curve is for dp squared, truly geometrical surface area. However, for unipolar charging, it gives us a curve which is not a square relationship. Now, Heinz figured out that if he were to multiply the geometrical surface area dp squared with the deposition curve on the lung, in the lung, alveolar for this case, he finds that all the data points actually fall right on top of this dp squared times the deposition curve. So therefore, we call this instrument measuring lung deposited surface area. But I think a lot of toxicologists doesn't like that. They said that why don't you just measure pure geometrical surface area? So during the last couple of years, we did try to do that. And what we did is to incorporate a electrostatic precipitator in between the unipolar charger and electrometer. And what we found is that under certain conditions, it is possible for us to obtain this truly geometrical surface area as a function of mobility diameter. So now we are taking a look at whether we can apply this to measure surface area of agglomerates. Now, in a recent paper that we published together with Prasinis and Fissan, the student did the numerical calculation, finding out that for agglomerate charging, most of the charges actually appear on the periphery of the agglomerates. And in the middle, there's hardly any charge particles. And so when we present it as a function of mean charge per particle, as a function of mobility diameter, so for sphere, this is the curve. And for the agglomerates, we find that is higher charge. Particles are charged to a higher degree for agglomerates. And then when we now put this charged particle into the new surface area monitor, and you can see that indeed this is for the sphere and this is for the agglomerates, which measure more surface area as a result. So we're still working on that, and so the student continue to work on this technique. Now the next irregular non-spherical particle or near spherical particle are viruses. And the virus aerosol is assemblies of virus carrying solid or liquid droplet suspended in the gas phase. Now they come from coughing, sneezing, talking, and it's important because it involves virus transmission and respiratory virus diseases. Now, what we like to find out in a couple of our paper here is to look at the ability of the carrier particles, whether it's cough droplets or other way of producing those particles, how it can carry ability of that with carrying virus particles and with survivability of those virus particle attached to the carrier particles. So the experiment we perform involve putting the virus in a colocin atomizer to spray it, and then put it into a conditioned tunnel, and then draw some of this into a DMA, where DMA will classify them according to mobility diameter. And when it come out, we collect it with a gelatin filter. Now for gelatin filter, we can put it in the water and it will totally dissolve. So then we can then recover all these live viruses. Now what we find is that the larger carrier particles will carry more virus particles. This curve demonstrates that. And then also the larger the carrier particles, the virus is capable of surviving longer. So these are the smaller carrier particles. They don't survive so well. But for the larger particles, carrier particles, the virus can survive for a longer time. Now, one of the ways to control viruses transmission is by respirator. So most of the current technique of evaluating a respirator is using sodium chloride aerosol through the filter media and then measure downstream with the photometer. So we would like to find out how good it is, the data obtained from those physical measurement applied to live virus protection. So here is the experiment that we did. We nebulized the virus particle and then sent it through a chamber with a respirator, and we measured the fractional penetration using an SMPS, and then we look at the virus infectivity using gelatin filter in the impactor. So here are a couple curves showing the penetration as a function of electromobility through the respirator. Now it has a typical invert V shape for filters with a peak around 50 nanometer. Now you can see here that for the human adenovirus and swine flu influenza, the penetration is very similar to physical penetration with a peak at 50 nanometer. Now, when we then look at the number concentration penetration compared with the overall infectivity penetration, we find that the virus infectivity penetration is at least 2 orders of magnitude lower than the physical penetration. So in a way, this is good that if the respirator is tested against sodium chloride particle, we know that it can protect you 2 orders of magnitude better than for virus particle penetrating through the respirator. Now, next, I'd like to talk about calibration. Recently, we received a project from Army Primary Standard Lab to calibrate OPC, optical particle counter, and CPC, condensation particle counter, at ultra low concentration. We're talking about as low as 10 particle per liter of air. And so we developed a technique of producing particles. In this case, we produce 3 micron PSL particle, and then split them. One go to the OPC under evaluation. The other one go to a deposition chamber. Now, for this deposition chamber, since it's 3 micron, so we just use gravitational settling to deposit the particle on an 8-inch silicon wafer. Now, in some other cases, for smaller size particle, we could use electric field as well. And once they are deposited, then we scan it with a wafer surface scanner. That's a very common instrument for the clean room. And then you can see that the scanner print out a map with all the particle collecting near the center of this wafer. And then they provide the total number count and sizing information as well. And here you can see that the concentration measured by the OPC agree with concentration on the surface scanner. This is the one-to-one relationship. So, so all this technique can be traceable to the NIST primary standard. So, in conclusion, I'd like to say that progress is made in developing methods for determining length, spherical, surface area, and fractal dimension of the non-spherical particles. More research is needed to automate this techniques or other new techniques into real-time instrument to facilitate the measurement. And there's also a need to develop a standardized technique for calibrating autonomous measuring instruments. So this is all that I have. Thank you very much.